Hello friends, myself Dr. Amit Bagde, Assistant Professor in Sharad Institute of Technology, College of Engineering, Yadra, Isalkaranji. Today we are going to discuss the very important topic of our engineering physics syllabus, that is dielectrics. So this is the content of today's lecture. That is first is introduction to dielectrics, second is the dielectric parameter, third is the type of polarization, fourth is the temperature and frequency dependence of dielectric material. So let us discuss the first point of our today's lecture is that is the introduction to dielectrics. A dielectrics is an insulating materials in which all the electrons are tightly bound to the nucleus of an atom. There are no free electrons available for in conduction of electricity. Thus, the electrical conductivity of dielectrics is very less, or ideally it is zero. The distinction between a dielectric material and the insulator lies in the application to which it is employed. The best example of dielectrics are glass, then polymer, mica, oil, and paper. So all the insulators are not dielectrics, but all the dielectrics are the insulators. So the insulating materials are used to prevent the electric flow of electric current to undesired locations, whereas the dielectric materials or the dielectrics are used to store the electric energy. So this is the main application of dielectrics. That is, the dielectrics are used to store the electric energy. Now, our second point is the dielectric parameter. So today we are today we are discussing the various dielectric parameters such as dielectric constant, electric displacement, polarization, polarizability. These are the dielectric parameters. So the first dielectric parameter is the dielectric constant. So it is observed that the storing of capacity of the capacitor, as we know that the capacitor is used to store the electric charge. Okay, so the storing capacity of the capacitor increases if the space between its plate is filled with dielectric material. Suppose C0 suppose C0 is the capacitance of capacitor in vacuum, and the C is the capacitance of the capacitor when the space between these two plates filled with the dielectric material. Then the dielectric constant of the material is given by K is equal to C upon C0. Okay, so this K is equal to C upon C0 is known as the dielectric constant, or K is known as the dielectric constant. Thus, the dielectric constant of a material, dielectric constant of a material is the ratio of capacitance of capacitor completely filled with the dielectric material to the capacitance of the capacitor of the same capacitor in vacuum. Now, in other words, the ratio of permittivity of the medium or the dielectric constant is nothing but the ratio of permittivity of the medium to that of the vacuum. That is, K is equal to epsilon K is equal to epsilon R is equal to epsilon upon epsilon 0, where Kr is the dielectric constant, epsilon R is the dielectric constant, epsilon R is the relative permittivity, epsilon is the permittivity of the material, and epsilon 0 is the permittivity of the vacuum. And permittivity is nothing but it is the storing capacity of the dielectric material is nothing but the permittivity. Okay, now our second parameter is the electric displacement. The electric displacement field in a material or dielectric material is defined as D is equal to epsilon naught E plus P, where this epsilon naught is the permittivity of the free space or vacuum, and E is the E is the electric field, and P is the polarization density of the electric material. So the electric displacement field is the vector field having unit coulomb per meter square, and the electric displacement is a vector field which describes the displacement effect of an electric field on the charges within the electric material, such as polarization charges or bound charges. So in short, it is the charge per unit area that would be displaced across a layer of conductor placed across an electric field. So this is the electric displacement, which is denoted as D is equal to epsilon naught E plus P. Our another third parameter is polarization. Okay, this is very important, polarization. uh, when the electric field, suppose E is the electric field, this E is the electric field. When electric field is applied to the dielectric material, which consists of positive and negative charges, the positive charges moves to the direction of the field, while the negative charges in the direction of the field. Okay, the displacement of these charges creates the local dipole. The displacement of these charges creates the local dipole in the dielectrics. So this process is known as polarization. Okay, I repeat this: when the electric field is applied to the dielectric material, which consists of a positive and negative charges, the positive charges moves towards the uh, moves opposite to the direction of the field, this direction, this direction, and the negative charges moves opposite to the direction of the field. So which creates the local dipole moment, local dipole in the dielectrics, which this process is known as dielectric polarization. So this figure shows the concept of polarization, and the polarization density is defined as the induced dipole moment per unit volume. And our next parameter is dielectric polarizability. Dielectric polarizability. As we know that when the electric material is placed in electric field, then the displacement of charges gives rise to the creation of dipole in the material. The polarization P is directly proportional to the applied electric field. That is, suppose P is the polarization. Okay, P is directly proportional to E. That is, polarization is directly proportional to electric field, or P is equal to suppose alpha into E. Alpha into E. So this alpha is the proportionality constant, which is known as polarizability, and its unit is farad meter square. Farad meter square. If the dielectric material contains n dipole per unit volume, then P is equal to n alpha into E. So this P is equal to n alpha E is the dielectric material, or the dielectric polarizability, uh, which contains n number of dipoles per unit volume. Now our our next point is types of polarization. uh, when an electric field is applied to the dielectric material, it creates or realigns the dipoles, which results in the polarization. As we know that the main type of polarizations are are the electronic polarization, ionic polarization, and orientation polarization. These are the three type of polarization which are occur in the dielectric material. Okay, now let us discuss the first uh, type, that is the electronic polarization. This figure shows the electronic polarization. Uh, a dielectric material has a large number of atoms, okay, having nuclei at the center and the electrons around it in a different orbits. When an electric field is applied, the nucleus moves away from the field while the electrons towards the field, okay, which creates the polarization, which creates the dipoles. Okay, therefore, there is a displacement there is a displacement which is less than the dimensions of the atom. So the type of polarization is called as electronic polarization. The electron polarization is independent of temperature, and the polarization is given by P is equal to N alpha E into E. So this is the polarization. This is the electronic polarization, where Pe is the electronic polarization, alpha is the electronic polarizability, N is the n number of dipoles, and E is the applied electric field. So this figure shows the electronic polarization. Here the displacement of this uh, ions is less than the dimensions of this atom. Now, the second type of polarization is ionic polarization. This figure shows the ionic polarization. This type of polarization occurs in an ionic crystal, such as sodium crystal. When the suppose is the electric field, okay. So when an electric field is applied to such a crystal or such a dielectric material, the polarization arises due to the displacement of the positive ions away from the field and negative ions towards the field. Okay. So the net process is that the ions are displaced in opposite direction until the ionic bonding forces stop this process. I am repeat this sentence. The net process is that the ions are displaced in opposite direction. The ions are displaced in a opposite ions are displaced in opposite direction until the ionic bonding forces stop this process. Until the ionic bonding forces stop this process. This way, the dipoles gets induced and is called as ionic polarization. Now, the polarization produced for a crystal having suppose n number of dipoles. So, ionic polarization is given by Pi is equal to n alpha I into Ai. So, this type of polarization also not depends on temperature. So, this alpha I is the ionic polarizability, is I is the applied electric field, and N is the number of dipoles, and Pi is the ionic polarization. Last one is the orientation polarization. Okay, this figure shows the orientation polarization. The orientation polarization is produced only in case of polar molecules. Polar molecules means having two different polarities, such as H2O, HCl. So this type of polarization is produced in only polar molecule, that is H2O, HCl, HCl, etc. Okay. So in this absence of external field, the dipoles are randomly oriented. This figure A shows in absence of electric field, that is E is equal to 0, the E is equal to 0, the dipoles are randomly oriented and they cancel the effect of each other. When the electric field is applied, these dipoles experiences a torque and try to align parallel to the applied field, which results in a rotation of dipole, which results in a rotation of these dipoles. So this is known as orientation polarization. So this type of polarization, and that is the orientation polarization, is strongly depends on temperature. Strongly depends on the polarization. So the net polarization is given or the net polarization for a crystal is given by P0. Suppose P0 is equal to N alpha 0 E I. So this P0 is the orientation polarization, N is the n number of dipoles in electric material, alpha 0 is the orientation polarizability, and EI is the applied electric field. So the total polarization is the P is equal to PE plus PI plus P0. That is, when the electric field is applied to the dielectric material, the total polarization is the sum of the electronic polarization ionic polarization and orientation polarization. This is the last point, that is the temperature and frequency dependence of dielectric material. The dielectric properties such as the polarization, dielectric constant, dielectric loss uh, depends on the frequency of applied electric field and temperature. Now let us discuss the first point, frequency dependence of dielectric material. When when AC electric field is applied to the dielectric material, the polarization of the material is a function of time. When AC electric field is applied to the dielectric material, the induced polarization of the in the dielectric material is a function of time. That is, P is equal to, sorry, P that is, suppose P is a function of time, that is polarization is a function of time, which is equal to P into 1 minus e raised to minus t upon tr. This is the polarization of the dielectric material, which is a function of time t. So P into function of time t, which is equal to P into 1 minus e raised to t upon tr, where this tr is the uh, relaxation time and P is the maximum polarization attained by the dielectric material due to the application of electric field, and tr is the relaxation time. So relaxation time for the particular polarization process during the application of the electric field, the relaxation time is the measure of the polarization process, is the time is the relaxation time is the measure of the polarization process, and is the time taken for a polarization process to reach the 67% of its maximum value, to reach the 67% of its maximum value. So this figure shows the frequency dependence of the polarization. This figure shows the frequency dependence of the polarization process. Here we seen that there are four type of polarizations, that is the space charge polarization, orientation polarization, ionic polarization, and electronic polarization. So the space charge polarization is the another type of polarization. This type of polarization occurs at a very low frequencies, that is less than 10 raised to 2 hertz. The space charge polarization is one of the slowest process, as we seen here. The space charge polarization is one of the slowest process as compared to the other type of polarization. Second is the orientation polarization. So this orientation polarization mechanism is faster than space charge polarization but slower than the ionic and electronic polarization process. So the orientation polarization occurs between the radio waves and microwave frequencies at room temperature. Next one is the ionic polarization. So the ionic polarization occurs at a frequency about 10 raised to 13 hertz. It is faster than the orientation and space charge polarization but slower than the electronic polarization. And last one is the electronic polarization. Electronic polarization is the fastest type of polarization, and this polarization occurs even at optical frequency, that 10 raised to 15 hertz. So uh, this is the graph of polarization against the frequency of the applied electric field. Okay. So this is a frequency dependence dielectric material. So from this graph it is seen that all type polarization is strongly depends on frequencies. And last is the temperature dependence of dielectric material. Temperature depend, as we know that the orientation polarization is produced due to the alignment of dipoles of the polar molecule in the presence of electric field. The increase in temperature disturbs the alignment of the dipoles due to the electric field. So this effect decreases the value of dielectric constant with increasing temperature. Okay. For example, suppose the dielectric constant of solid HCl decreases from suppose 19 to 14 when the temperature is increased from 100 to 160 Kelvin. At its melting point of 160 Kelvin, it drops to 12. So this is also due to the fact that the molecules per unit volume decreases due to the expansion of on melting. Okay, so the other type of polarization, that is the electronic polarization and ionic polarization, not affected by the temperature. Thus the value of dielectric constant that remains unchanged with change in temperature. Okay, that is only the orientation polarization is strong, because the orientation polarization is strongly depends on temperature, not by electronic and ionic polarization. Thank you. So this is the part of dielectrics. So we have discussed now this is the summary. Now today we discussed about the introduction of dielectrics, dielectric parameter, type of polarization, frequency and temperature dependence of dielectric material. Thank you.